Lunar Prospector. Lunar Prospector was the third mission selected by NASA for full development and construction as part of the Discovery program. At a cost of $62.8 million, the 19-month mission was designed for a low polar orbit investigation of the Moon, including mapping of surface composition including polar ice deposits, measurements of magnetic and gravity fields, and study of lunar outgassing events. The mission ended July 31, 1999, when the orbiter was deliberately crashed into a crater near the lunar south pole after the presence of water ice was successfully detected. Data from the mission allowed the construction of a detailed map of the surface composition of the Moon, and helped to improve understanding of the origin, evolution, current state, and resources of the Moon. Several articles on the scientific results were published in the journal Science. Lunar Prospector was managed by NASA Ames Research Center with the prime contractor Lockheed Martin. The principal investigator for the mission was Alan Binder. His personal account of the mission, Lunar Prospector, Against All Odds, is highly critical of the bureaucracy of NASA overall, and of its contractors. The spacecraft was a graphite epoxy drum, 1.36 m in diameter and 1.28 m high with 3 radial 2.5 m instrument booms. A 1.1 m extension boom at the end of one of the 2.5 m booms held the magnetometer. Total initial mass was 296 kg. It was spin-stabilized with its spin axis normal to the ecliptic plane. The spacecraft was controlled by 6 hydrazine monopropellant 22 Newton thrusters. 3 fuel tanks mounted inside the drum held 138 kg of hydrazine pressurized by helium. The power system consisted of body-mounted solar cells which produced an average of 186 W and a 4.8 Ah rechargeable NiCad battery. Communications were through 2 S-band transponders, a slotted, phased array medium-gain antenna for downlink, and an omnidirectional low-gain antenna for downlink and uplink. The onboard computer was a Harris 80C86 with 64 KB of EEPROM and 64 KB of static RAM. All control was from the ground, the computer echoing each command to the ground for verification there. Once the command was ground verified, an execute command from the ground told the computer to proceed with execution of the command. The computer built telemetry data as a combination of immediate data and also read from a circular queue buffer which allowed the computer to repeat data it had read 53 minutes earlier. This simple solid-state recorder ensured that all data collected during communications blackout periods would be received, providing the blackout was not longer than 53 minutes. The probe also carried a small amount of the remains of Eugene Shoemaker, astronomer and CO discoverer of comet Shoemaker-Levy 9, to the Moon for a space burial. Following launch on January 7, 1998 UT aboard a 4-stage Athena 2 rocket, Lunar Prospector had a 105-hour cruise to the Moon. During the cruise, the 3 instrument booms were deployed. The MAG and APS collected calibration data, while the GRS, NS, and ER outgassed for 1 day, after which they also collected calibration data in cislunar space. The craft was inserted into an 11.6-hour period capture orbit about the Moon at the end of the cruise phase. After 24 hours, Lunar Prospector was inserted into a 3.5-hour period intermediate orbit, followed 24 hours later by transfer into a 92 km x 153 km preliminary mapping orbit, and then on January 16 by insertion into the near-circular 100 km altitude nominal lunar polar mapping orbit with an inclination of 90 degrees and a period of 118 minutes. Lunar calibration data was collected during the 11.6 and 3.5-hour orbits. Lunar mapping data collection started shortly after the 118-minute orbit was achieved. The data collection was periodically interrupted during the mission as planned for orbital maintenance burns, which took place to recircularize the orbit whenever the periselene or aposelene was more than 20 km to 25 km from the 100 km nominal orbit. This occurred about once per month. On December 19, 1998, a maneuver lowered the orbit to 40 km to perform higher resolution studies. The orbit was altered again on January 28 to a 15 km x 45 km orbit, ending the 1-year primary mission and beginning the extended mission. The mission ended on July 31, 1999 at 9 hours 52 minutes and 2 seconds UT when Lunar Prospector was steered into a deliberate collision in a permanently shadowed area of the Shoemaker crater near the lunar south pole. It was hoped that the impact would liberate water vapor from the suspected ice deposits in the crater and that the plume would be detectable from Earth. However, no such plume was observed. The Lunar Prospector mission was the third mission selected by NASA for full development and launch as part of NASA's Discovery program. Total cost for the mission was $63 million including development, launch vehicle, and operations. The spacecraft carried 6 instruments, a gamma-ray spectrometer, a neutron spectrometer, a magnetometer, an electron reflectometer, an alpha particle spectrometer, and a Doppler gravity experiment. The instruments were omnidirectional and required no sequencing. The normal observation sequence was to record and downlink data continuously. The Lunar Prospector GRS produced the first global measurements of gamma-ray spectra from the lunar surface, from which are derived the first direct measurements of the chemical composition for the entire lunar surface. This data effectively mapped the distribution of various important elements across the Moon. For example, the Lunar Prospector GRS identified several regions with high iron concentrations. The fundamental purpose of the GRS experiment was to provide global maps of elemental abundances on the lunar surface. The GRS was designed to record the spectrum of gamma rays emitted by. The most important elements detectable by the GRS were uranium, thorium, and potassium, radioactive elements which generate gamma rays spontaneously, and iron, titanium, oxygen, silicon, aluminum, magnesium, and calcium, elements which emit gamma rays when hit by cosmic rays or solar wind particles. The uranium, thorium, and potassium in particular were used to map the location of creep. The GRS was also capable of detecting fast neutrons, which complemented the Neutron Spectrometer in the search for water on the Moon. The gamma-ray spectrometer was a small cylinder which was mounted on the end of one of the 3 2.5 m radial booms extending from Lunar Prospector. It consisted of a bismuth germanate crystal surrounded by a shield of borate plastic. Gamma rays striking the bismuth atoms produced a flash of light with an intensity proportional to the energy of the gamma ray which was recorded by detectors. The energy of the gamma ray is associated with the element responsible for its emission. Due to a low signal-to-noise ratio, multiple passes were required to generate statistically significant results. At 9 passes per month, it was expected to take about 3 months to confidently estimate abundances of thorium, potassium, and uranium, and 12 months for the other elements. The precision varies according to element measured. For U, TH, and K, the precision is 7% to 15%, for Fe 45%, for Ti 20%, and for the overall distribution of creep 15% to 30%. The borate plastic shield was used in the detection of fast neutrons. The GRS was designed to achieve global coverage from an altitude of approximately 100 km and with a surface resolution of 150 km. Based on the Lunar Prospector Neutron Spectrometer data, mission scientists have determined that there is enough evidence for lunar water ice in the polar craters of the Moon, an estimated 3 billion metric tons. The NS was designed to detect minute amounts of water ice which were believed to exist on the Moon. It was capable of detecting water ice at a level of less than 0.01%. The Moon has a number of permanently shadowed craters near the poles with continuous temperatures of 190 degrees C. These craters may act as cold traps of water from incoming comets and meteoroids. Any water from these bodies which found its way into these craters could become permanently frozen. The NS was also used to measure the abundance of hydrogen implanted by solar wind. The Neutron Spectrometer was a thin cylinder co-located with the alpha particle spectrometer at the end of one of the 3 radial Lunar Prospector science booms. The instrument had a surface resolution of 150 km. For the polar ice studies, the NS was slated to examine the poles to 80 degrees latitude, with a sensitivity of at least 10 ppm by volume of hydrogen. For the implanted hydrogen studies, the NS was intended to examine the entire globe with a sensitivity of 50 ppmv. The Neutron Spectrometer consisted of 2 canisters each containing helium-3 and an energy counter. Any neutrons colliding with the helium atoms give an energy signature which can be detected and counted. One of the canisters was wrapped in cadmium, and one in tin. The cadmium screens out thermal neutrons, while the tin does not. Thermal neutrons are cosmic ray-generated neutrons which have lost much of their energy in collisions with hydrogen atoms. Differences in the counts between the 2 canisters indicate the number of thermal neutrons detected, which in turn indicates the amount of hydrogen in the Moon's crust at a given location. Large quantities of hydrogen would likely be due to the presence of water. The alpha particle spectrometer was damaged during launch, ruining one of the 5 detecting faces. Additionally, due to sunspot activity peaking during the mission, the lunar data was obscured by solar interference. The information was eventually recovered by subtracting out the effects of the solar activity. The APS was designed to detect radon outgassing events on the surface of the Moon. The APS recorded alpha particle signatures of radioactive decay of radon gas and its byproduct polonium. These putative outgassing events, in which radon, nitrogen, and carbon dioxide are vented, are hypothesized to be the source of the tenuous lunar atmosphere, and may be the result of the low-level volcanic/tectonic activity on the Moon. Information on the existence, timing, and sources of these events may help in a determination of the style and rate of lunar tectonics. The APS was a cube approximately 18 cm co-located with the neutron spectrometer on the end of one of the 3 radial 2.5 m Lunar Prospector science booms. It contained 10 silicon detectors sandwiched between gold and aluminum discs arranged on 5 of 6 sides of the cube. Alpha particles, produced by the decay of radon and polonium, leave tracks of charge on the silicon wafers when they impact the silicon. A high voltage is applied to the silicon, and the current is amplified by being funneled along the tracks to the aluminum disc and is recorded for identification. The APS was designed to make a global examination of gas release events and polonium distribution with a surface resolution of 150 km and a precision of 10%. The Doppler gravity experiment was the first polar, low-altitude mapping of the lunar gravity field. The Clementine mission had previously produced a relatively low-resolution map, but the Prospector DGE obtained data approximately 5 times as detailed, the first truly operational gravity map of the Moon. The practical benefits of this are more stable long-term orbits and better fuel efficiency. Additionally, the DGE data is hoped to help researchers learn more about lunar origins and the nature of the lunar core. The DGE identified 3 new near-side mass concentration regions. The purpose of the Lunar Prospector DGE was to learn about the surface and internal mass distribution of the Moon. This is accomplished by measuring the Doppler shift in the S-band tracking signal as it reaches Earth, which can be converted to spacecraft accelerations. The accelerations can be processed to provide estimates of the lunar gravity field, from which the location and size of mass anomalies affecting the spacecraft orbit can be modeled. Estimates of the surface and internal mass distribution give information on the crust, lithosphere, and internal structure of the Moon. This experiment provided the first lunar gravity data from a low polar orbit. Because line-of-sight tracking was required for this experiment, only the near-side gravity field could be estimated using this Doppler method. The experiment was a byproduct of the spacecraft S-band tracking, and so has no listed weight or power requirements. The experiment was designed to give the near-side gravity field with a surface resolution of 200 km and precision of 5 mgal in the form of spherical harmonic coefficients to degree and order 60. In the extended mission, in which the spacecraft descended to an orbit with an altitude of 50 km and then to 10 km, this resolution was expected to improve by a factor of 100 or more. The downlink telemetry signal was transmitted at 2273 MHz, over a plus or minus 1 MHz bandwidth as a right-hand circularly polarized signal at a nominal power of 5W and peak power of 7W. Command uplinks were sent at 2093.0542 MHz over a plus or minus 1 MHz bandwidth. The transponder was a standard Laurel/conic S-band transponder. An omnidirectional antenna can be used for uplink and downlink, or a medium-gain helix antenna can be used. Since the spacecraft was spin-stabilized, the spin resulted in a bias in the Doppler signal due to the spacecraft antenna pattern spinning with respect to the Earth station of 0.417 Hz for the omnidirectional antenna, and 0.0172 Hz for the medium-gain antenna. LOS data was sampled at 5 seconds to account for the approximately 5-second spin rate of the spacecraft, leaving a residual of less than 0.1 mm/s. The magnetometer and electron reflectometer detected anomalous surface magnetic fields on the Moon, which are in stark contrast to a global magnetosphere. The Moon's overall magnetic field is too weak to deflect the solar wind, but MAG/ER discovered a small surface anomaly that can do so. This anomaly, about 100 km in diameter, has therefore been referred to as the smallest known magnetosphere, magnetosheath, and bow shock system in the Solar System. Due to this and other magnetic features of the Moon's surface, hydrogen deposited by solar wind is non-uniformly distributed, being denser at the periphery of the magnetic features. Since hydrogen density is a desirable characteristic for hypothetical lunar bases, this information may be useful in choosing optimal sites for possible long-term Moon missions. The electron reflectometer and magnetometer were designed to collect information on the lunar magnetic fields. The Moon has no global magnetic field, but it does have weak localized magnetic fields at its surface. These may be paleomagnetic remnants of a former global magnetic field, or may be due to meteor impacts or other local phenomena. This experiment was to help map these fields and provide information on their origins, allow possible examination of distribution of minerals on the lunar surface, aid in a determination of the size and composition of the lunar core, and provide information on the lunar-induced magnetic dipole. The ER determined the location and strength of magnetic fields from the energy spectrum and direction of electrons. The instrument measured the pitch angles of solar wind electrons reflected from the Moon by lunar magnetic fields. Stronger local magnetic fields can reflect electrons with larger pitch angles. Field strengths as small as 0.01 nt could be measured with a spatial accuracy of about 3 km at the lunar surface. The MAG was a triaxial flux gate magnetometer similar in design to the instrument used on Mars Global Surveyor. It could measure the magnetic field amplitude and direction at spacecraft altitude with a spatial resolution of about 100 km when ambient plasma disturbances are minimal. The ER and the electronics package were located at the end of one of the 3 radial science booms on Lunar Prospector. The MAG was in turn extended further on a 0.8 m boom, a combined 2.6 m from Lunar Prospector, in order to isolate it from spacecraft-generated magnetic fields. The ER and MAG instruments had a combined mass of 5 kg and used 4.5 watts of power.